In this video, we're going to explore using mass percent of a sample to find the empirical formula and identify a possible species for an unknown sample. So here's 3 carbon oxygen hydrogen containing compounds. I have ethanol, I have formic acid, and I have 1122 tetrahydroxyethylene. Fancy molecule names aside, I have 15 grams of this sample that were sent out. It was processed, and they came back and said that I had 26.1% carbon, 4.4% hydrogen, and 69.6% oxygen. So we're going to find which of these is a possible match by empirical formula. In this case, we do happen to know, as they were provided to us, the formulas for these compounds, so we could find the mass percent of each of these and compare it to solve which one it would be. Often, though, we don't know exactly what the formula is to start with. We don't know all the molecules we could build out of it. And so until we know the number of each element, we can't come up with which organic molecules it could be. And so finding that empirical formula helps us start to figure out which type of things we ought to be looking at. Because if we actually look at these formulas, C2H6O, CH2O2, and C2H4O4. These are reasonably different, though 2 of them do actually share a lowest whole number ratio. I could divide this one by 2, I'd get 1 carbon, 2 hydrogens, 2 oxygens. So A is a very different empirical formula from B and C. So let's see if we can figure out which of these this might be, or which of these it definitely isn't. Well, if I have mass percent and the mass of a starting compound, I can find what weight of those 15 grams was actually carbon. And so I could take 15 grams of sample, I could multiply it by the decimal form of 26.1%, so 0.261, and I could find a weight of carbon in those 15 grams. And I'd find that it was 3.915 grams of carbon. Do this for hydrogen, well, there was 15 grams total, and 4.4% is 0.044, which will give us 0.66 grams of hydrogen. And for the oxygen, there's 15 grams of sample and 0.696 for fraction form of 69.6%. We'll find there was 10.44 grams of oxygen. I actually find the weight of each element that was in our sample. I then can use that to find the moles of it. Knowing our weight ratios doesn't tell us how many of each thing there is, though. Oxygen just weighs more than hydrogen and carbon. So having 10 grams of oxygen doesn't tell us if that's more or less number of oxygen versus hydrogen and carbon. And so I need to convert each of these. I need to turn my weight of carbon into moles. Well, there's 12.01 grams of carbon in 1 mole of carbon. And for hydrogen, there's 1.008 grams of hydrogen in 1 mole of hydrogen. And for my oxygen, there's 16.00 grams of oxygen in 1 mole of oxygen. So 0.653 moles of oxygen, 0.655 mole of hydrogen, and 0.326 mole of carbon. If I then set that up to find the empirical formula, I'd say, well, there's carbon, there's hydrogen, there's oxygen, there's 0.326, there's 0.655, and 0.653. The lowest number of moles in the formula is from the carbon, so I divide them all by 0.326. That'll give me a single carbon. I'll give my hydrogens 2.009 and my oxygens 2.003. Figuring with a little error in our measurements, that's pretty much 2 and 2. So this is 1 carbon, 2 hydrogens, 2 oxygens. So this is a C1H2O2. If we go back and look at our formulas, my first formula does not have more hydrogens and oxygens than carbon. So A is out. The empirical formula does not match the formula for A. C1H2O2, it does work for B, but remember we could divide C by 2 and also get C1H2O2. So this also works for C. The percentages we get out of our 15-gram sample fit for both compound B and compound C. The empirical formula alone cannot tell us this. It does tell us that it's one of these two. We'd be left to do one more experiment to have to determine which of these it is. There are ways to tell the molecular mass. In the modern era, we can spray just a little bit into a mass spectrometer, and they can identify the molecular mass of a compound incredibly well and very quickly. Yay for modern technology. In the old days, you could solve this with an H tube, where you'd put some of the unknown in one side, and you'd put some known amount of salt in the other, and then you'd fill them both with water. And depending on which one had more moles of things, the water would move in one direction or the other. A little bit would evaporate until the concentrations were the same, until the same number of moles were dissolved in the same volume. So if you had half as many moles on one side, you'd end up with half the volume, so that it'd be the same concentration as the other side. Using this, you could solve it. Yay for modern technology. We can find a molecular mass nice and quick. And so if I tell you the molecular mass was 46.0, we could then identify that, okay, B is the only thing that follows both of those. A also had a molecular mass of 46. If all we did was use the molecular mass, we wouldn't have been able to tell between A and B. We needed the empirical formula. So between those two pieces of data, the empirical formula from the mass percents and a modern technique to get molecular mass quickly, we can identify that this is indeed formic acid, which if you've ever been bitten by an ant, this is what the burning sensation is.